In this video, we're going to look at limits, derivatives, and integrals involving the function y equals the natural log of x. We can use the rules of logarithms that we've derived in the last section to prove the following two limits. The limit as x goes to infinity if the natural log of x is infinity, and the limit as x goes to 0 if the natural log of x is minus infinity. And to establish these two limits, it's enough to look at a sequence of values of x approaching either infinity or 0 for which the limits are true. And this is because the function y equals the natural log of x is continuous, and this is something we've already established. So let's do that. Last day we saw that it was pretty easy to show that the natural log of 2 is bigger than 1/2 with a simple Riemann sum. And now we can take a sequence of x values approaching infinity, namely x equals 2 to the m as m increases without bound, and see what happens to them. We have the natural log of 2 to the m by the power rule is m times the natural log of 2, and by the above inequality that must be greater than m over 2. But remember, we can take m as large as we like, and therefore the natural log of 2 to the m increases without bound, and the limit as x approaches infinity of the natural log of x is infinity. And we can do something similar. As x approaches 0, we can take the sequence of values 1 over 2 to the n, which certainly approaches 0 as the integer values of n get larger and larger, and the natural log of 1 over 2 to the n is minus n times the natural log of 2 by those rules of logarithms, and that has to be less than minus n over 2, because remember that inequality above reverses when we multiply across by minus. Therefore, as this sequence of values 1 over 2 to the n approaches 0, the value of the natural log of 1 over 2 to the n decreases without bound, and we can conclude that as x approaches 0, the values of the natural log of x approach minus infinity by continuity. Let's look at an example. How would we calculate the limit as x goes to infinity of the natural log of 1 over x squared plus 1? This is the composition of two functions, the function 1 over x squared plus 1, followed by the function the natural logarithm. And the first thing to think about is what happens the function inside of the brackets 1 over x squared plus 1 as x approaches infinity. Using Calc 1 techniques, we see that x squared plus 1, a polynomial, approaches infinity as x approaches infinity, and therefore 1 over that approaches 0 as x approaches infinity. Now we can reshape this limit by a substitution. So if we let u equals 1 over x squared plus 1, we have the limit as x goes to infinity of the natural log of 1 over x squared plus 1 is the limit of the natural log of u as u approaches 0. Because we've established that as x approaches infinity, u approaches 0. And now this limit, we already know, it doesn't really matter what we call the variable. The limit as u goes to 0 of the natural log of u has to be minus infinity from our previous deductions. Now here's an important function which is related to the natural log of x, except it has a bigger domain. Remember, 1 over x is defined for negative values of x, but we've only found the antiderivative, the natural log of x, when x is positive. So the natural log of x is only defined for positive values, but we can extend the domain by looking at the natural log of the absolute value of x. Again, remember that the absolute value of x is really a piecewise defined function in a single expression. So the natural log of the absolute value of x is also a piecewise defined function, and we've written down its full definition here. It's equal to the natural log of x if x is positive, and the natural log of minus x if x is less than 0. And notice this is an even function. The natural log of the absolute value of x equals the natural log of the absolute value of minus x for every x. And remember, the graph of an even function is symmetric around the y-axis. So we just need to draw half of the graph, namely that part to the right of the y-axis, in order to see what the whole graph looks like. The other half of the graph is equal to the mirror image of what's to the right of the y-axis. So using the graph of the natural log of x, which we've already looked at in detail, we can find the other half of the graph of y equals the natural log of the absolute value of x, and we show the full graph here. Now, the natural log of the absolute value of x is also an antiderivative of 1 over x, but this is true for all x values where x is not equal to 0. And you can verify that. We know that the derivative of the natural log of x is 1 over x for x greater than 0, and the derivative of the natural log of the absolute value of x for x less than 0 is the derivative of the natural log of minus x, and using the chain rule we see that that's 1 over minus x times minus 1, which is 1 over x. So we get two new rules. The derivative with respect to x of the natural log of the absolute value of x is 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x plus c. So this gives us a more complete antiderivative of 1 over x. Now we can also apply the chain rule for differentiation to our previous derivative rule. We get the derivative with respect to x of the natural log of the absolute value of g of x for any function g is going to be 1 over g of x times the derivative of what's inside that absolute value sign g prime of x. Well, we can apply this, and rather than memorizing that rule, it's much easier to memorize how to apply the chain rule. Suppose we want to differentiate the natural log of the absolute value of sine x. Then, proceeding with the chain rule, it's 1 over what's inside those absolute value signs, 1 over sine of x, times the derivative of what's inside the absolute value sign. And that's equal to cosine of x. So we get the derivative is cosine of x over sine of x. Here's another application of the chain rule, and before I actually apply the chain rule here, I'm going to simplify this function. The natural log of the absolute value of the cubed root of x minus 1 is equal to the natural log of the absolute value of x minus 1 to the power of 1 over 3. So I can use the power rule to reshape that. I'm looking for the derivative with respect to x of 1 over 3 times the natural log of the absolute value of x minus 1. And I get that that's equal to 1 over 3 times 1 over what's inside the absolute value signs times its derivative. So that's 1 over x minus 1 times 1. So finally, the derivative of that function is 1 over 3 times x minus 1. Now we can reverse those two rules of differentiation, and we get two rules of integration. So now the integral of 1 over x dx is the natural log of the absolute value of x plus c. That's a more complete description of an antiderivative for that function. And I could reverse the chain rule from before to get the integral of g prime of x over g of x is the natural log of the absolute value of g of x. Sometimes this is applicable in a very straightforward way, but it's good to know how to use substitution if it's not obvious that this is what's happening here. Suppose I want to find this integral, the integral of x over 3 minus x squared dx. Well, a natural substitution to make would be u equals the denominator here, 3 minus x squared, and I have du equals minus 2x dx, or x times dx, which I want to replace in that integral, is du over minus 2. And now I can replace everything by something involving a u. X dx is minus du over 2, and 3 minus x squared is u, and I end up with the integral of 1 over minus 2u du. And now this is easy. I pull out that 1 over minus 2, or minus 1 over 2, and I get the integral of 1 over u du, which is the natural log of the absolute value of u, and I end up with minus 1/2 the natural log of the absolute value of u, and replacing the u by 3 minus x squared, my final answer is minus 1/2 the natural log of the absolute value of 3 minus x squared plus c.